Okay, well, this meeting. There are many things I could say about this, including what a wonderful lunch we've had. Just spectacular. My goodness. And then the desserts, the berries and whipped cream, and oh. So there are many different talks the past couple of days on a variety of topics. I'm going to change gears again. This is something completely different. I've spent my life in manufacturing, worked for GE Healthcare and Thermo Fisher Scientific. And I'm going to be speaking about how to design green facilities and how to better manufacture vaccines in a more environmentally friendly way. So the title, Net Positive Economy in Vaccine Manufacturing, and I'll define for you coming up what I mean by net positive. So looking at vaccine manufacturing per se, just to get started, there are so many types and manufacturing modes in vaccine manufacturing. We've got animal tissues we use, like chicken eggs. We've got bacterial fermentation-based vaccines, prokaryotic and eukaryotic cell culture in bioreactors. There's cell-free in vitro transcription. And I've made a list myself over on the right here of so many different types of vaccines. And when we say types, it depends on what categorization, what organization you're looking at. The indication, the molecular structure of the vaccine, the way it works, the way it's delivered. And so I've just made a list of random categories of types of vaccines. But the manufacturing of them obviously then is implicated in all these distinctions of vaccine types. So the talk today is on sustainable manufacturing. And just to introduce what goes into more sustainable manufacturing, we've got materials and supply chain, and we want to make that greener. We've got the process and the equipment involved. We've got the facilities themselves and the service to the facility. And when I say service, I mean electricity and water and things like that. And then, of course, there's waste reduction, the simply working on how to produce less burdensome waste. But they're all categories of approach. And it's an area of distinct study. I've got a meeting over on the right here that focused on this particular topic. So as I have in the title, Net Zero Facility Design, in the title I have Net Plus Facility Design. We're going to start off with Net Zero Facility Design. And these are buildings that achieve net zero energy or carbon or resource consumption. They're facilities that generate as much resource as they consume over a specific period of time. And as you see in the talk, there are a lot of overlapping definitions and criteria in the definitions that have to be examined. Because if you say you want to generate less carbon, for example, you can say, well, when do you start measuring it? Do you start measuring it when you break ground to build the building? Do you end finishing it when you've disposed of the container that the physician used in the dosing? What's the time frame on the examination of, for example, carbon? So we have to consider what stresses, what environmental burdens we're measuring, and when we're measuring them, and over what specific usages. An important element in looking at net zero facility design is the integration of energy efficiency, renewable energy, and sustainable practices in the whole process. So, I'm sorry. What's happened here? So moving on from net zero to the title, Net Positive Facility Design. These are buildings that produce more energy or water or resources than they consume. They go beyond the net zero goals and they contribute surplus resources back into whatever ecosystem you're examining. And they accomplish it using basically the same approaches that we use in net zero design, and we're going to go through some of them later on. So before we do, though, you may ask, well, why? Why do we want a net positive value for individual manufacturing facilities? Isn't net zero good enough? Isn't it good enough not to contribute to environmental burdens? Isn't it good enough to be neutral, to not contribute to any degradation? Well, there are three main reasons why people are advocating net positive design. One is to compensate for facilities that can't be net zero. There are some facilities that it's impossible to generate as much fresh water or electricity as is consumed in the facility. Things like aluminum smelters or even hospitals would have difficulty generating as much energy requirement, for example, or purifying as much water as they require. So because we're looking at an ecosystem in a society, whether you're looking at a town or a state or a province or a country or the entire world, we not only want to be net zero for a particular concern like an individual or a facility, but we want to be overall net zero. So to compensate for this, we talk about net positive. Another reason for net positive design is to compensate for the energy involved in building the building. Because of process intensification and continuous manufacturing, we found that the efficiency of producing many vaccines has increased tremendously over the past 20 years, sometimes orders of magnitude. This makes the environmental footprint of manufacturing much smaller than it used to be. And without any change then, the burden in building and the construction of the facility then becomes a greater proportion of the overall environmental burden. So looking at greener building facility construction approaches is now even more interesting from an overall net, for example, carbon burden perspective. And the other is that because of artificial intelligence and machine learning and application and their application in things such as a digital twin, we find that building information modeling now provides tremendous power in accomplishing more efficient building design and reducing the environmental footprint. Oh, I'm sorry, I got to do both. I'm having trouble again with the slides. Yeah, oh, thank you. So, okay, if anyone's interested in pursuing net positive design, what I've discovered in researching myself is that there are many different terms used for the same, well, similar concept. And again, each of these terms, well, many of these terms have a slightly different scope, a slightly different application. For example, carbon negative means that the building, the facility is consuming carbon. It's not releasing carbon, it's not neutral, it's actually taking in carbon from some environmental source. Whereas plus energy buildings are buildings that produce more energy than they consume. But it's all the same idea that the building is not only not an environmental burden, it's not neutral, it's assisting in some ways. And probably net plus would be the most general type of term because you haven't defined what you mean by it. But the difficulty in saying something like net plus is people would say, well, are you referring to energy or carbon or water or what? But anyway, these are all terms you could use. Some important concepts in defining these relationships that I've introduced the complexity on is over on the right-hand column here, process-induced environmental burdens. And these are the local on-site burdens that are produced when you're actually running the plant. And many people only think of this, or when you first address the topic, you think about for example, power consumption in running a bioreactor, or the waste solutions that are emitted when you're harvesting many eggs. But there are other scopes to be concerned about. For example, the environmental product footprint are all the burdens arising from the product, including the building, the materials, transportation, usage, disposal of the container that the material is shipped in. There's the building embodied energy. That's what I referred to earlier, the power, the resources it took to construct the building, and therefore the environmental footprint of the construction itself. And another concept to look at is referred to as life cycle assessment. And there are two elements to life cycle assessment. One are all of the environmental or potential environmental burdens that it examines, and I've got a list here, things like greenhouse gases, acidification, ozone, ecotoxicity, other air pollutions, particulates, water pollution. So a life cycle assessment would consider all of these types of toxicities, and there are between 15 and 25, depending on how you break them up, to consider. The other thing about a life cycle assessment is that you will carefully define the cradle to grave concept, what the scope of the product activity, the production activity or the product itself is under consideration, and it must be defined. So what are the tools that we use then to achieve this net positive design? One of the concepts that come to mind at first is energy. People think about, of course, if we're looking at being green, electricity, fossil fuels, how are we going to drive the energy in the plant? I've got 3 columns here in all of my, the resources that we're considering here. The approach, the benefit or value, and the objections, because there aren't any universally accepted answers to any of the approaches used in green manufacturing. Green municipal service is an approach to powering the plant. If you live in an area that gets its power from hydroelectric, for example, that's a nice thing to have. Where I come from in Utah, we get the majority of our power from burning coal. So you would say, well, a green municipal service is an advantage, and be content with it. But what's happening now when we consider things like energy plus buildings is that usage of even a sustainable power source depletes it from the general town or region that you're in, making it unavailable to people who might not be able to replace it with a green source. So just the fact that you have it available to you doesn't mean you want to avail yourself of it. And this is a consideration that isn't obvious at first. On-site wind and battery. For example, using windmills and batteries to power the plant. Sounds like a good idea. Some people are concerned about windmills, about emitted energy, fields, harm to birds, noise, site pollution. There are objections to it. Let's just move down to the bottom, and I can't spend too much time on each slide. But like, for example, nuclear. Nuclear is a very controversial power source now. It was universally heralded in the 50s. It became really an anathema after Fukushima. I mean, there was 3 Mile Island and the one in Ukraine, which I've forgotten. But after Fukushima, people really didn't want nuclear anymore. But because of new nuclear designs, better nuclear designs for classical approaches, and the need for reduction in carbon footprint and reliable energy, now it's back into consideration. So the benefits are that it has very low carbon during operation, and the concerns obviously are failures and hazards. So then moving down to the process equipment itself. Electrification of equipment is a big goal, is a big consideration in process and facility design. And of course, we see in the benefit and value, reduced fuel consumption, reduced CapEx, maintenance. There are a lot of advantages to electrification. But, as I described in my locale, our electricity is produced with fossil fuels, so you're really not immediately gaining that much. other than the potential for, if you're an electrified facility, you have the potential then for a greener municipal source, and then availing yourself of that advantage. Automation is a big driver. There are so many advantages to process automation: reduce footprint, increased efficiency, reduce personnel. We're looking now at facilities that have extremely low personnel demands. Often a tenth of what the old process used to employ. And one of the criticisms of that type of a process is that you only need a tenth of the employees, and people are complaining about the fact that automation is taking away jobs. So as you can see, there aren't any easy solutions. Every solution, every benefit has a negative consideration. So in the construction and build, sustainability by design is a new buzzword for organizations to have teams and prioritized directives to consider sustainable manufacturing approaches. The advantage here is that from the top, every team involved in the activity knows that it has a commission to reduce environmental burdens and to be greener. But the concern there is that if it is a sincere and acted upon priority, that it can distract from other goals, such as financial goals. The 3 through 7D modeling, we'll talk about that coming up. So recycling and demolition waste, for example, using setting concrete as a construction aggregate. What's going on now is people will take an old building, big enormous concrete building, and they'll grind that up and use it as the grit for fresh concrete. And it's really a significant saving, because not only is producing gravel an energy-intensive activity, but then shipping in the new gravel and shipping away the old concrete is an environmental burden. So we don't have time to go through any more, but you can see there are many activities that are making the actual construction of the building greener. Okay, so digitalization in Pharma 5.0. Moving to paperless operations, it's obvious. If you get rid of paper, one of the helps there. But of course, it's expensive if you're not in a greenfield, new construction, new process development. If you're trying to transition an existing process to make it greener, you've got the hysteresis here of having a very good, well-established paper system that has to be replaced with the digital. And then moving down to continued process to control and multivariate statistical process control at the bottom. Reduces error and rework, supports process intensification. There's so many advantages to the newer process control, but there is the cost of development and the new personnel that might be required. So Industry 4.0 and 5.0, there's, on the right-hand side, I've got a history of industrial development in the world in general, and we're moving now between 4 and 5, where we have advances in cloud technology, automation, robotics, artificial intelligence. 5.0 is the next goal, where we have efficient, smooth. I'm not going to go through all the lists. You can scan through them with your eyes as I speak. But in 5.0, the idea is that ultimately a plant operator will enter the manufacturing operation. The walls will all be digital and display what's going on. He'll take a look around. He'll talk to the room. He'll say, how are things going? And the artificial intelligence will say, everything's nominal. I'm watching a potential in approaching deviation in reactor 4, but I'm taking activity to avoid it, and I think everything's going to be fine. Then I could say, well, what's going on in 4, and what are you doing, and have this dialogue, and that's what we're going to see, what we can see now, but what we will see practically in the future, and that's 5.0. And then there'll be processes that have to be done by hand, But the operator can put on gloves that have sensors, and what they call a cobot. So he'll move his hands and he'll see digitally what's going on either in the next room or in Mars or wherever. And the cobot will be manipulating the instrument just as he is in this more controlled space. So that's where we'll be going for green activities. So I'll drill down a little bit into AI and ML applications. Of course, they encompass a wide range of digital technologies, networking, data types. We heard a little bit about AI and ML in this meeting already. But I want to encourage us to consider that machine language, for example, is a lot like calculus or like a handheld calculator. It's a tool that can be applied in many different categories and applications. Just as that cartoon of the blind man and the elephant, and the man who's holding the one leg says it's like a tree, and the man who's holding the tail says it's like a rope. We're doing that with artificial intelligence. People know a particular application, they're using ChatGPT, and they think AI is a large language model, which it does support. But it does so many other things in many different ways. I think what I'll skip down to my key at the bottom and spend a minute on that. It can provide fast, multivariate, and point-to-point analysis, something that we're really lacking in a lot of process control. Many of the systems that are used, even in computerized computer-controlled processes, look at averages and don't regard the individual activities of for example, cells in a bioreactor. But we have the ability now to examine what's going on a cell-to-cell basis, and we want the maths to be able to follow that. Okay, so it's not a singleplex, but a true multiplex. On another angle, there are many operations that they call them multiplex, but actually we're looking at each individual curve separately and acting on it. But here there's actually a synergizing, the ML will allow you to consider the individual vectors of each rate and the implication of it in, for example, an advanced model. And then there's the power of dimensionality reduction, yet maintaining the information that existed in all these higher dimensional systems. You can have 50 parameters acting in one activity, but AI can now reduce the dimensionality of that consideration without losing the power of the information that was being contributed by all of these different concerns. So then looking at one particular AI application, what's called a digital twin. I don't know here how many people know what a digital twin is or a digital shadow or have had experience. But some of the things that they're providing are manufacturing execution systems and process control with real-time analysis and real-time carefully judged activity to improve and maintain the process under control. They can be used in process optimization, depending on the data that is available to both train and operate the digital twin. It can come up with creative solutions to process optimization. It's powerful in quality control, in decision to support, in supply chain management. I'll speak a little bit in the future about how the power there. And predictive maintenance and resource allocation. The digital twin is an active, dynamic model of the equipment or process or facility, and operates it as a wise individual who has instant access to a lot of information. So we talked about defining some of the issues in developing a green building. Some of the tools that we'd have, the categories of green activities and for example, the electrification of equipment to see how we're going to make it greener, how AI and advanced modeling techniques can help us to make more efficient processes. And I'm going to talk a little bit about building information modeling and how we can make greener buildings using some of the newer tools. There's a picture on the right here. Whoop, I'm sorry. I've got two different computers going here. Picture on the right of a two-dimensional model of a building, you know, the old days of drafting on paper. Then we all are aware of three-dimensional modeling, where we've got a computer simulation and we can rotate it in 3 dimensions and look at, get a lot more power in developing. But we can move now into higher levels of modeling, incorporating more than 3 dimensions. And the terms that are used are, for example, building energy modeling the energy demands and distribution throughout the building. And a universal scene description is a powerful computing tool used in supporting all the dynamic aspects of a facility. And just to expand a bit about that, on building information modeling, there's a history of how it developed, and then there's the goals of where we're going with it. But one of the key points is that it's a collaborative process. People can work from different locations, even around the world, and contribute to this modeling in real time. So we have many different engineers with different specialties working on the plans at once. And I'm running out of time here, so I think maybe I can just end on this slide. So they've described the current state and goals in building information modeling in levels and dimensions. So level 3 is that we have access to these plans, and the development is shared across a variety of shareholders. You can imagine level 2 was basically the same type of approach that had to be done iteratively and be passed around. So level 3 is it's shared, and level 4 is now using AI and digital twins and digital models to synthesize many processes within the building dynamically. So 4D BIM focuses on the function and changes over time. 5D adds production budgeting and costs over time. 6D then looks at the environmental burden and sustainability factors in the design of the facility and processes. And then 7D models the operations and maintenance of the plant. So you can see when we get to 7D is what I was describing earlier with a digital twin that has this overriding real-time activity considering all of these elements of the building's operation. So I'm going to not talk about, I'll conclude then summarizing that the goals and the value in net positive facility design is that it's growing in popularity, it extends net zero goals, and it uses all of the established tools, but towards the idea that we live in a community and we not only want to be greener within our own person or processing plant, but contribute to the general society and help assist those that can't be net zero. Well, thanks very much.
So, because you point out digital twins, and we're also trying to use digital twins in healthcare, one of the issues in healthcare is we don't have it as well defined in terms of processes and components and interactions as we might have it in engineering. Mm-hmm. But I wouldn't say that we actually have everything modeled perfectly in engineering either. Do you see how you can take operations of a building with its digital twin and come up with diagnostic procedures for the gaps that might translate to being applied to healthcare.
Yeah, well, I just came back from last week from BPI West, where I heard a fantastic presentation on artificial intelligence being used in the establishment of patient histories and diagnosis through an interactive large language model called Amy. That's working well. It's progressing. We're not done. But yes, in both medical activities and in the sustainability of medical institutions such as a hospital, everything I've described today will apply in a hospital setting with a little tweaks. But as I've defined, the power of, for example, a digital twin in contributing to the operation of a process or facility is not limited at all to any particular design or activity. It's programmed by the data of the actual process itself, and it does become a directed intelligence and limited to that scope, but it begins as a blank slate and learns the particular, for example, hospital facility. Okay. Well, thanks very much.